So we will take a look at different distributions, some of which you have already know, some you may have seen it before. So let's take a look and let's try to find situations that it could occur. First, normal distribution. Right? Normal distributions is a distribution that symmetric, right? That is symmetric. It has two parameters, mu and sigma square, right? Variance. Mu here specify the location, right? The center of the distribution. So for example, this one, mu equals 0. So you have the graph having highest peak at 0. And this one, the green line, mu equal -2. So the center point here is at -2. So mu indicate the center location, right? Central value, right? Sigma square or variance indicates the spread or the scale of the distribution. So the larger sigma square, the wider the mountain would be, right? The wider the distribution would be. It indicates the scale. The smaller sigma square indicate the narrower distribution, right? So as you can see here, the higher sigma square from 0.2 to 1 to 5, the base of the distribution becomes wider and wider. So that's the sigma square, the variance. So this is normal distribution. Normal distribution occur if you have enough data, and then mostly data would kind of looks like this normal distribution. But sometimes some process, when you have small data set, it would be described as certain distribution. But after your data sets grow larger and larger, the distribution can be approximated by normal distribution. One misconception about normal distribution that have been going all over the world, I would say all over the places, is the usage of mean, right? Mean is often used to explain all the average value. Mean is often used to explain like the expected value or the values that everyone would have, right? That's usually is the concept of mean that has been used widely. The problem is that mean would be valid only for symmetric distribution. If the distribution, no, I would say symmetric and have reverse bell shape. Because if the distribution doesn't look like this, for example, if it looks like this one, well, mean would be center point for sure, but it would be center point of nothing because you have like two peak here, and that why mean might fail. Also, in real life, data usually behave not in normal distribution way. You would have something like a skewness to the distribution, and that skewness would screw up this distribution, this normal distribution, and screw up the mean. It would kind of invalidate the means because it would drag the mean up. Mean is so sensitive to outliers. If you have a lot of outliers, a lot of skewness, mean will be pulled up. Right? So this is normal distribution, right? The one that is well known, but mostly have been used wrongly. So, okay. Next one, let me check. Right. Next one is the exponential distribution. For the exponential distribution, I want you to this exponential distribution. I want you to mark this as well because we will come back to this again when we take a look at the different another distribution that is also an inverse of this distribution. Exponential distribution explain the probability of finding value in exponential functions. So this is the exponential function. It means that you will see most of the occurrence of the values at the low value, and only some of them would have high values. Okay, so it is explained by this exponential function. As x grow, this value would be reduced to 0, right? As x approach, as x like limit value, x approach infinity, this would be minus infinity, and 1 over minus infinity would become 1 on this one. This become minus infinity, e to the minus infinity is actually approaching 0. Okay, so that's why you have the graph approaching 0 value here. The exponential function is used to explain the process that having lots of value accumulate at the low end here. A process like if you measure inter-arrival time, the time that that maybe different customer arrive, or if I measure the time between two cars passing through the checkpoint, right? That time would be really short. Like if I use minutes to explain to represent that. So if one car coming in and another car coming in, the inter-arrival time between two cars would be very small, right? And most of them would be clustered toward very low value. So exponential distribution is usually used to explain such a process. That is, you have a constant rate of instance coming in or passing through, or if it is usually used in model network in the sense of computer network. Like you can have like a queuing system that customer coming to the queue or packet come to the queue and then being processed and then go on, and another packet coming in. Inter-arrival time between the packet would be in the exponential distribution. Right? Cumulative distribution looks like this one. So if you plot histogram or density function of the graph and you see it looks like this one, you can think about exponential distribution. It might be it. And if it's the time measurement or something similar to that, well, can be explained with this. The parameters, all right. Parameters of exponential distribution is this lambda, okay? Lambda value here plays roles here. You have e to the minus lambda x. If lambda is larger, you will have a steeper slope, a steeper decline. That means a lot of value would be clustered toward the low value. If lambda is larger, you have the slope that is shallower, okay? Lambda is often be thought of as, I think you also passed the circuit class, right? Lambda sometimes is thought of as 1 over tau. And in engineering, tau here is the time constant of the exponential value of exponential decay, the time constant. Like the time constant of temperature reduce, when that the one that you learn in the physics class, or in circuit class, time constant of the electrical discharge, half-life, also time constant. So it represents the same thing. Inverse of that would be the rate of change, right? The inverse of the time constant would be the rate of change. So you can think about this as the rate of change. The larger value here, the larger lambda here, you have larger lambda, you will have the value approaching infinity faster. That means the value should be reduced to 0 faster. Well, I think this one might be wrong, because if lambda equal 0.5, I think this one is wrong. You can try it out, because larger lambda should increase the rate. If it increases the rate, then you should go down faster. So the color might be wrong though. You please check this. Maybe you can try it out on yourself, right? Okay, so that's exponential distribution. So what I'm not sure is whether the picture is correct or not, because my hunch is that larger lambda, you get larger rate of decay, then the graph should approach zero faster rather than slower like this one. So if it's wrong, revise and then fix it, right? You can think about this as part of your lab, try it out. Okay, that's the exponential distribution. Now, exponential distribution has just one parameters. These parameters can be thought of as the scale, some similar to this variance value, because it kind of control the spread of the distribution. There's this distribution that contains two types of parameters, right? That instead of like normal distribution, gamma normal distribution have the location parameter and the scale parameter. Gamma distribution contains two parameters: the shape parameters and the lambda and the theta parameters. Here, the scale parameters. Shape parameters. When the shape parameters change, the shape of the distribution will change. Like this one. If k equal 1, you got something that is similar to exponential distribution. If k increase, or if k is less than 1, like the purple line here, you got a steeper exponential distribution. But once k increase, like k become, yes? Any questions? Right, so if you have questions, don't hesitate to click raise hand and then ask, all right? Once k increase, like this 2, the distribution would now becomes log. It will become kind of normal distribution with skewness, right? But when k increased further and further to become 9, it now look more like the normal distribution. So the shape parameters, I didn't put the function here. You can take a look at the equations, the full equation of gamma distribution, which is quite complicated. I can guarantee online. But what I want you to know is the effects of these parameters first. When you know the effects and then you take a look at the equations, you understand it more, understand the equation more. But you need to understand the effect of parameters to explain the distribution first, and then you can move on further. So when k becomes larger, the distribution, like 7.5 here, the distribution now look more like normal distribution. So it means that you can use gamma distribution quite flexibly and to explain different types of data set. Now, when we take a look at another parameters, let's look at scale parameters. The scale parameters, when it has value equal to 2, like this, comparing to the black line here, which has the lambda, the theta equal 0.5, you can see that the tail of the distribution is shorter when you have lambda at the low value. But when, theta at the low value, the scale parameter at the low value. When the scale increase, the distribution also spread to the right-hand side. So that would mean that the theta value, the scale parameters, control the size, the scale of the distribution, while k control the shape of the distribution. When we look at other distribution, you will see a lot of distribution that behave this way, right? Why do they create these types of distribution, like gamma distribution? Because it is useful and flexible in a lot of cases. It can be used to explain a lot of process mathematically and the actual physical process, right? So as something that is quite similar to gamma distribution, this is called the Weibull distribution. The Weibull distribution is used a lot in explaining the reliability process. In reliability engineering, the engineer would want to understand how reliable the process are. Like if you have this device, you want to know whether this device will expire, when will it expire. You want to know whether the products that you have, what should be the warranty period of the product that you have. In order to identify those values, you can fit the data set to the Weibull distribution. Right? In the Weibull distributions, the distribution also contains two parameters, very similar to gamma distribution. The first one is the shape parameters, and the second one, lambda here, is the scale parameters. So instead of having theta, now we have lambda as scale, and we have the shape parameters controlling the shape of the distribution. So when you take a look at the distribution here, if you change the shape of, if you change the value of k from 2 to 3 to 4, the distribution would shift from the green to the blue and to the magenta, right? Here. So when you increase, this one might be better, right? In terms of explaining k. If k is less than 1, so similar to gamma distribution. If k is less than 1, you got something that is akin to exponential distribution. But when k is more than 1, like 1.5 here in the magenta, you got something that is like the log normal, and then when k increase to large value, you got almost like normal distribution. Now, if you compare and for the scale distribution, when you increase the scale value, when you increase scale from 0.5 to 3, you can see that the distribution shift to the right hand side. Okay. Comparing to gamma distribution, they are quite similar to a certain extent. But what you can see here is that the shape distribution, when it's only 5, you got almost like this normal distribution. While for gamma, when k is 5, you'd have something that is still having rightward scale a bit. So I think this is a property that is why Weibull distribution is often used in reliability engineering, because it can approximate the different phase of the product, like this one, exponential decay, often used to explain the process of the number of error that you find, or the number of fault that occurring in development. It should go down like this one. Normal distribution is often used to explain maybe the lifetime of the device. If it's normal, it should kind of broken down at a certain point of time. So different value of shape parameters has been used to explain those processes. So this is Weibull distribution. Right, these are the continuous distributions, examples of continuous distribution that you should look for. You can see that to understand this distribution, you need to take a look at the parameters, right? The parameter and the shapes of the distribution once the parameters change. All right, and next, let's take a look at some of the distribution in the discrete size. This is Bernoulli distribution, or you may know it as Bernoulli trials, or in your stat class, you will know it as tossing the coin, get head or tail. You have two outcomes, right? Getting one outcome, success, and another outcome, failure. And these outcomes would have probability associating with them. Okay, so you have certain chance to get 1 and another certain chance to get 0. This is the Bernoulli distribution. When you have multiple Bernoulli distribution, multiple Bernoulli trials, then you have the distribution that is like the number of success that could happen would be binomial distribution. In binomial distribution, you have n, the parameters indicating the number of trial, and you have p. P indicate the chance of success of the Bernoulli trial. So simplest example of this one is the one that you learned in your stat, like tossing coin 100 times. But let's think about it different way. You can have probability of catching COVID-19 and say people, there are 100 people, so we want to know probability of 10 would catch that, so you can calculate the distribution out of that. So how to look at this distribution? X-axis here is the number. So this is for this is scale from 0 to 40, which indicate the number of positive case that you will find. Okay, the number of hit that you will find, and for different parameters, you would have the chance that you can obtain this differently. So what does it mean? It means that if you try it, for example, if you try with p equals 0.5, n equals 40, a lot of time, right? Doing this trial, 40 run trial, 100 times, you have histogram that looks like this. Right? The histogram will look like this. You have a lot of time, you end up at about 20. So this is why we have higher value here. Okay, and if you and if you have like here p equal 0.5 n equal 20, you see that the peak here occur at 10. It's about n times p, and that's the mean of the binomial distribution. How to use this one? Think about yourself as Thai Airways, which is almost in bankruptcy right now, as an airline, and then you have the there is a certain chance that the passenger might not turn up at the airport because they might have not been able to catch the flight. There might be traffic jam. So there might be like 1% that the passenger who already check in might not come to the airport. If that customer does not turn up at the airport, it doesn't mean that the ticket is invalidated, right? The customer still would be able to use that ticket to fly another time, but that would mean that the airline would get an empty seat, and that is not good. So the probability of customer turning up and the number of passenger that would turn up to the plane, you can think of that like N and P. N is the number of passengers. P is the probability of not turning up. So airline would fly a lot of time. If you accumulate their data, the data should look like this binomial distribution. And then airline can then identify and find a way to maybe reduce the probability of turning down, or use that in a simulation to identify how to cope with that, maybe creating some types of dynamic pricing. What would happen, they can find out in the simulation rather than just imposing the policy directly. Right? So this is binomial distribution. You got Bernoulli and binomial. And next is another quite useful distribution. This is the Poisson distribution. Right? The Poisson distribution is the distribution that expresses the chance to get the value, the count value, given a number of events occurring in a fixed interval of time. For example, you want to count the number of, if you take the COVID-19 data and then you create a model of the people catching or the people that has been diagnosed as having COVID-19, and then plot the distribution, you see that the distribution of the people having that data, that symptoms at because we have like daily measurement, right? The daily detection, it will behave like this Poisson distribution. I would use data from China because the case has almost already been resolved there. But for us and for Europe, for US, we still are in the like early phase of that. Might be slower for us, but story will be different in other countries. So you can plot the distribution. The probability of count of the count number would behave like Poisson distribution. Okay, so you need to have a fixed amount of time. right? Fixed interval of time, and then you count the number. So what type of thing that you can do with that? I can count the number of cars passing through the road at for each hour, and that would be Poisson distribution. I can count the number of customers coming to the store for each day. That would be Poisson distribution. And that would mean if you know that, you can create a simulation. We will talk about it next time. In your game, suppose you want to create games that is like real life, you can measure this data and then create simulation out of this. So you got customer coming in at this amount, at this number each day. If you create a simulation games, or if you want to create a simulation model to emulate what would happen next year, feel free to use this distribution to explore that. Poisson distribution is an inverse of the exponential distribution. You can see that they are kind of like one another because Poisson distribution count the number of events. Count the number of events occurring in a fixed interval, right? You got fixed interval, and then you kind of count the number of time that it happens. Why? If I go back to the exponential distribution, this one measure the time between two events, right? The time between two events and the number of times happen, frequency and time. So that's why they are inversely in proportional. Actually, they are an inverse concept to one another, like Poisson and the exponential distribution. Right. So what does it mean? You can model the same thing. For example, if you create sim hospital games and you want to know, you want to create a customer coming to hospital, right? What you want to find maybe like, or you want to simulate the number of patient happening. Then what you can do is to either count the number, you can count the number, and then this will be the number of events occurring in that interval of time. Or you can simulate the next time event, right? You can simulate, in camera should look like this, next time event. This event happened, you want to know when the next event would happen. You want to kind of guess the value, this value out. That would be exponential distribution. And if you get this value out and count that in time, number of time, then you get Poisson distribution. So like I said, frequency and time is kind of inverse of one another. There are functions that can be used in R to simulate this distribution. For the uniform distribution, you can think of uniform distribution as having the same chance. So uniform distribution is usually used to explain like noise in that happen in nature, but mostly not in uniform in real life. Discrete uniform, you can think of like tossing dice and others that have the similar chance. Theoretically, lottery should be uniform distribution. But is it true? Maybe I'll leave that to your project if you want to do that, right? Analyzing the chance that things number would turn out. Should be uniform. If not, then, well, there might be some defect or some certain dependency in the mechanism to get while turning up. Normal distribution, there's a function called rnorm. For discrete uniform, it's RDUnif. Exponential, there's REXP, gamma is R gamma, Bernoulli, or binomial, there's R Bernoulli, and Poisson is R Poisson.